Very good morning to you. It's Dean from Mathstar Observatory. Guys, in this video we're going to be trying to quantify the universe. For some people it's going to be a little bit of a treat. For some people, they're not bothered because they have their own little bubble and it's more important than the big picture, and that is very much what we're looking at here, is trillions and trillions of galaxies in just a small section of our universe. So we'll talk about quantification, simplifying things, and you'll be very surprised how you can simplify everything you're looking at there, and there's a lot to look at there in a little while. But before we do, as usual, a really big thanks to those people that are supporting our observatory and enabling us to bring the data to the people, and hopefully encourage 98% of those people that aren't aware of a rare anomaly that's taking place in their life. So one of the things I like about science is it very much is all about pulling things apart and understanding how they work. And you can think of some very gruesome things that has happened in science, like pulling animals apart to see how they work and what is their function, and studies of brains and things like that in monkeys. That's one way science learns, but another way science learns is by examination of objects. If I said to you, simplify what you're looking at right now, quantify what it is you see in amongst everything that is there, and to a lot of us it just looks like a load of paint splattered on a black background. But if we started to zoom in on some of these galaxies, we'd see that there was a lot more going on. Let me see if I can find some images for you. So here we are, just looking at one of those little blips of light in that picture, only we've zoomed in a little bit. So it's a little bit like a fractal pattern. It's one of the reasons why I like the Mandelbrot equation and some of the fractal patterns that come out of that. So we're looking at a spiral galaxy, and we live in a similar spiral galaxy, but again it just looks like millions of little bits of light swirling round in time. And if we was to be in a position to have a look at a galaxy, it would only be if we viewed it for perhaps a few light years that we'd actually see that it was actually swirling and turning round. But trying to quantify something at this level would be very difficult. You'd have to zoom in a lot closer than that, and we're going to do that to try and find out what it is that makes all this possible. But right at this point, if I said to you, quantify it, how would you go about that? Would you say, well, this is something made up of all the atoms on the periodic table, so say 114, 115 different atomic nuclei can make up that? Well, that would be correct. But if I said simplify it a little bit more than that, some might go, okay, well, all this is electrical. We can examine it on different wavelengths, so it's part of the electromagnetic spectrum. But you could quantify it even easier than that if you wanted to, because if I said to you, everything that you're looking at in this picture, right, and I mean if we go right down to the very smallest part, it's not just electromagnetic, it is also described very easily as two things: dielectrics and conductors. And that is probably the closest examination of anything like this that you'll probably, or a description of anything like this that you're ever going to earn. You've probably never come across that description ever mentioned to you, but it is very, very true. It's either going to be a conductive material or it's going to be a dielectric material, and I think that simplifies things at a micro scale very accurately. So to give you a better understanding, I think this electromagnetic frequency chart gives us a good idea of what we're talking about. So you can see the sine wave at the top of the chart, and it starts to get closer and closer each wave as it goes down towards gamma rays. So the radio waves at building levels are quite large, as you can see, and then we go to humans, they start to get a little bit closer. We're into the microwave length of frequency, or amplitude, and then the amplitude, if it remains constant like it does in that chart there, we see just the frequency increasing. So we go into the infrared, where we're past butterfly size wavelengths, and then we go into needlepoint wavelengths. As we go down a little bit more, we get into the visible light spectrum, into photons that are the little particles that don't really have any measurable mass but can travel at the speed of light and only are moved by such things as black holes. That's why I say they do have a small amount of mass, but otherwise a black hole would never affect it. And then we go into the ultraviolet, where we get down to molecules, and then into X-rays, where we're at the atomic scale, and then we go into gamma rays. So we're then going into the atomic nuclei, which are the the elementary particles that make up atoms. And the only thing that's not put on this chart is a further quantification of things that are all made up, that make up our universe or ourselves. And that would be, how do we simplify it past atomic nuclei? How do we split things down so nice and easy? Well, we could go into the atomic nuclei as we've looked at this chart, and we would see neutrons, protons. We broke them apart, we're going to start seeing other subatomic molecules like muons, leptons, and electrons and things like that. We're going to keep going down, but we're still in the electromagnetic frequency range. And then we will get to, how do we then quantify what it is that we're looking at. And I suppose people are going to say, well, we can go into the dielectric and the conductive, and what I'm talking about there is dielectrics are things that don't allow electricity to pass through them. Conductives are things that allow electricity to pass through them, and I think that is breaking it down to its very last components. We're probably going to find, as has been described in science, things that are positively charged, things that are negatively charged, again dielectrics and conductives. And we can probably go on the other end of that. We could say, well, you might find that something is magnetically attracted. Well, it should be, because all these things are making up part of the electromagnetic spectrum, so they've got to have those two abilities about them. They've got to be electrical in nature and magnetic in nature, and then they will attract each other at some point, because they're either electrically charged and something's negatively charged. They're going to pull each other together. I just wanted to give you just a brief description of breaking things down, how science works and stuff like that. And I think what we've done is a very quick example of that. We've looked at the universe, we broke it down to, we just examined then, if we zoomed in a little bit more to one of the galaxies, we know that in those galaxies there are millions of stars. Some of them have a lot of planets surrounding them. Some of them, like ours, have 9 planets surrounding them. If we start looking at the planets, we'll start to see on further examination that as we get into the planet, we probably hit the atmosphere first. We can sample that, have a look at what's in the composition of the atmosphere, what atoms are there. We can examine what atoms are beneath the atmosphere on the planet, and we can then start to examine even more things at a smaller scale. And that's when we start going down into the rocks, having a look at what the rocks on the surface are made of. And then we go further into the rocks, we have a look at what the actual molecules are in there, and then we have a look at the atoms that are there, and then we have a look at the atomic nuclei within the rock, and then we see that we keep going and going and going. What we find is that we find that there is something common about everything that we've looked at so far. It's all it's all part of the electromagnetic frequency, and everything therefore in our universe is electric and non-electric, or a conductive or a non-conductive or a dielectric. Here's a quick look at the periodic table, and as far as we've been able to discover, nothing else in the universe exists other than what's on this periodic table. There may be some very exotic elements or atoms that we've not probably discovered, but their short life or their instability means that they don't hang around for very long, and they very quickly decay into other different things. When they break down, they change into different nuclei or elements even in themselves. But pretty much we can categorize or quantify these in a lot of different ways, like noble gases. We can say that some are dielectrics and conductors, some are gases, some are liquids, some are solids. There's lots of ways of, or actinides if you want to go down that road, and there's lots of different ways of categorizing these things. But if you want to just split it down into two things and focus on those, we'll find that we can easily do that by saying dielectric and conductive, and that is probably it. We can start smashing these down to subatomic elements or elementary elements, and we're going to find the protons, neutrons. We start smashing those up, we're going to find even smaller particles, right down to what CERN believe they have recently discovered is the boson Higgs. So we go down to muons, leptons, quarks, those sort of things. You start bringing it all back up to as we start going up the macro scale, because we're now looking at the micro scale, we start to build things with these. So if we take all those elements on the periodic table and put them together and add a massive quantity of them, what we'll eventually get is probably interstellar gas. And after millions and millions of years, that interstellar gas will start to electrically configure itself so that particles start to stick together, forming small masses, which then have a gravity, and then those masses will attract larger or more of those smaller objects, and it will build up like a snowball does in your hand when you keep gathering more and more snow. And what you end up with eventually is a new solar system forming, and that's what we're looking at in this picture. This is a very, very early stage of a new solar system forming. You can see the star there in the middle with a lot of interstellar gas around it, but you can already see some of the planets that have formed around that star, and eventually you'll end up with a new solar system. And after millions and millions of years, when things have settled down and cooled down, you end up with solar systems like ours that consist of Mercury, Venus, then our planet, the third one from the Sun, Earth. Then we go Mars, Jupiter, Saturn, Uranus, Neptune, and then finally Pluto. And we've also got in between these planets asteroid belts. You've probably heard of them, Kuiper belts, or the Oort belt. These are debris fields that consist of all the leftover, or planets that wasn't perfectly in line with their rotations around the Sun or their orbits around the Sun, and they've collided and left these big debris fields that we see there today. But sometimes very beautiful things can happen in solar systems, and the elements can be in the right place at the right time. And what I'm talking about now is, if you've already guessed, we're talking about our planet, which is at the right distance for water to be liquid. Not too far away where it'd be ice, not too close where it'd be gas, but in a liquid form. And that's what enables, really life to begin. And there's a couple of things in planetary mechanics that need to be put in place for a unique thing to happen. So not only does a planet have to be at the correct distance away from the sun in order for it to have water on its surface, it also has to have a dynamo which generates a magnetic field around the Earth that protects it from all the harmful radiation, not just coming from our sun, but entering our solar system from the galaxy we're in, and also other galaxies. Particles don't stop; they keep travelling. They're like there's in space. There's nothing to stop them unless they collide with something, and then you'll probably get whatever reaction from that. But the point of all this is that we get an understanding of, our beautiful world, our beautiful place in our solar system, our beautiful place in our galaxy, and our beautiful place in this universe. And you know what? It's only been the last probably 300 years, really, that we've started to learn about the vastness of, our home in this universe. And the gathering of the information over the last 300 years has been described as, when we try to find out new things, has been described as simply science, and something I'm really passionate about. And you can apply this in a lot of different areas. We've got biology, chemistry, physics, mathematics, all different ways of examining objects to find out, what the truths are of those objects that we're examining. And this is what we do at the observatory. What we're focused on in science is the behaviour of a planet, or other planets for that matter, but we do live on Earth, and it is going through a unique change, so it's a perfect opportunity for someone that has an interest in the geomagnetics and the processes of Earth's going through magnetic reversals. It's a perfect opportunity to get in there and see what is going on based on all the information that we have got around us. And sometimes we don't have all the information, and therefore we start to try and find ways of gathering that information, like we have done here at this observatory. That's why I say, guys, what we do at the observatory is unlike any other channel. We have actually used scientific methods to go out there, get the information on this anomaly that is a really rare one. Last time 780,000 years ago, super rare anomaly, and no data to this point other than what has been collected recently by large organisations and organisations globally, and then even little observatories like ours that have been out there collecting the data ourselves, because these organisations have literally taken taxpayers' money and not shared the information. It's a common thing that happens these days, with a lot of things. But that's what really we're interested in. And we're trying to gather as much information to understand what even a magnetic pole reversal is all about. And there's a lot of missing data, so we're trying to find methods of collecting it, and hopefully we'll at some point in the near future witness the processes of a magnetic reversal, and what happens when one of the critical things that allows us to be alive on this planet to start with changes. Will those changes be permanent, like what happened on Mars? Will our magnetosphere, after it goes into its weakest form, just collapse, never come back up? It happened to our nearest neighbour partner, Mars. It lost its magnetic field, lost its atmosphere, lost its water on its planet. Is that a possibility for us? Well, yes, of course, because we don't know why there's been such a large delay in the last reversal. So, we have to have that on the table as a possibility, that we could be looking at something slowly leading us in a direction to losing that critical thing that keeps our planet alive. Yes, water's important. the magnetosphere is equally important, because these two components allow life to form on a planet. And any one that's into astrophysics will tell you that we live on a very unique planet, and for that reason alone, when you think about the magnetic reversal, you then understand how significant it is. And for me to realise that a while ago, I'm talking over 10 years now, and then try and get in on it and study as much as we can about it is really exciting for me. And I know that a lot of people have interest. I know that we've not reached a lot of people in informing them that this Earth is going through a magnetic reversal, but we can do our best. And so long as you keep trying to do your best, I think you will get some results out of that. And I believe we have got some fantastic results to date. And if we can keep that going, then we can only build upon what we've gathered today, and we can expand the knowledge of what we understand about this event, and we get a clearer picture. Like this video has took us from the macro of looking at the universe to examining galaxies, then solar systems within the galaxies, and then going right down to the last detail in understanding the periodic table, all the elements that make up all what we see today, and then going a little bit further to examining, just or quantifying what those elements could be easily separated into, and we find that it's dielectrics and conductors. And then we go back out and we end up with really fascinating components of those elements. So I know today's video has been a little bit different, and I really hope you've got something out of it. But really what we're about is the changing of our planet in the terms of the magnetic reversal. That's where we focus ourselves on here at the observatory. And we just ask that if you want to help support us and keep us going, there's a link down there in the description. And the only other thing to say is, guys, you look after your loved ones today. Have an amazing day, and I'll say what I usually do. Bye for now.